Okay, in this problem we're flying in a jet in room temperature air, impossible, at a speed of 200 meters per second, and pass a flock of geese and is headed in the same direction at 20 meters per second. So I've drawn the geese here. They're going the same direction, 20 meters per second. You're going 200 meters per second. This is not the scale. And after you pass the geese, you emit a signal of 450 hertz. Okay. Now, with a picture and a brief statement, explain why they hear a different frequency. Include the name of the phenomena. Well, of course, you know this is the Doppler effect. And a picture. So 450. If you imagine that as this sound is being emitted, this continues to travel, you will end up seeing, if you looked at the front of the wave, right around the plane, something like this, and since the plane is moving into the in that direction, you're getting the sound waves which are moving away from the source. You're getting the sound waves all bunched up at the front end, the direction of travel, and kind of stretched out at the other end. So what this set of circles is meant to indicate is really the wave front that is moving at the sound of speed, velocity equals 340 meters per second, away from the source. So the source again was 450 hertz. Now the geese are headed into that, but why they hear different frequency? Well, the frequency that you hear will be the frequency of encountering these waves here. Okay, so let's just remind ourselves what is it the frequency that we hear. We know the velocity equals the frequency times the wavelength, and when you hear sound, the frequency that you hear is the frequency that you basically hit each one of these guys like this. So this is the wave front, and if the geese were standing still and this were moving, you'd hear, and the plane were not moving, these circles would be concentric, and they would be moving at a speed of 340 meters per second. Okay, now the plane moves. Okay, and so what happens is the source of the sound is actually further away. So even though that continues, the sound waves continue to move out at 340 meters per second, the wavelength in effect is stretched out over here. So this wavelength is longer than it would be for the 450 hertz. Okay, well, what is that wavelength? Okay, it's something longer than that. Therefore, the velocity remains the same, but the wavelength is bigger. Therefore, the frequency should be less. Now, we've got this complication that we're traveling towards the waves at 20 meters per second, but that's not going to be enough to compensate for this 200. This 10 times slower than this. So the frequency will be less than 450 hertz, the ones that the geese hear. Okay, what is the wavelength of the sound waves approaching the geese? Okay, let's compute that. Let's see, the wavelength, the velocity equals the distance traveled, the wavelength divided by the period. Let's figure out what the period is. So the period from this 450 hertz, the period will be 450 hertz is 450 cycles per second. Therefore, the period is 1 over 450 seconds per cycle. And what is the wavelength? The velocity is the same. Okay, hold on a second. Okay, how I might do this is I would say if it weren't moving at all, what would be the wavelength? Well, in this time period, well, we know the velocity is 340 meters per second equals 450 per second times lambda. So lambda is equal to 340 over 450. 340 over 450, about 34 over 45 meters. Okay, so let's see. So this lambda with no plane is 35 over 45 meters. But now we add the speed of the plane. So this is moving at 200 meters per second. So in the same period, 1 over 450 seconds, this plane moves 200 meters per second times 1 over 450 seconds is about 200 over 450 meters, or 20 over 45 meters. Is that right? 20 over 45. 20 over 45. Interesting. Okay, so so this plane adds 20 over 45 meters to the wavelength in the same period. So the wavelength is now 35 over 45 plus 20 over 45 is 55 over 45 meters, or let's see, that's 1 and 10/45, or roughly 1.25 meters is the wavelength. Okay, this last question, what frequency do the geese hear? Well, if they weren't moving at all, they would basically hear the velocity of the sound equals the frequency times this 1.25 meter wavelength. That would be the frequency. But they are moving, aren't they? They're moving towards the sound, so they're going to hit the frequency actually is going to be higher than what they would hear if they were just standing still. Now, what is that going to be? Okay, I'm going to need a clean sheet for this. I'm going to just go ahead and clear this. Here we go. We know that the geese are moving at 20 meters per second. The sound that gets to them has a wavelength of 1.25 meters, and this velocity of the sound is 340 meters per second. Okay, so what we know is the velocity equals the frequency times the wavelength. We know this wavelength to be 1.25 meters. What is the frequency? Well, what is the velocity here? Well, it's the combined velocity of coming at the sound plus the sound moving in this direction, the waves moving in this direction, 340 meters per second. The velocity now is 340 plus 20 meters per second. And that equals the frequency times this 1.25 meters. So that is 360 meters per second divided by 1.25 is the same thing as 5/4. I'm just going to write it this way. 5 divided by 4, I'm going to move the 4 up there, equals the frequency. So that is roughly 8/10 of 360, which is equal to, what is that? That is 360 minus 720. No, it's minus 72. About 200, 300, 290. Let's call it 290 hertz is the frequency that the geese hear.